Good evening to all of you. Hope you all are doing well. Okay. Today we have with us Dr. Rajiv Jain sir, and it's my privilege to introduce him on this platform. Dr. Rajiv Jain sir is a senior scientist of forensic toxicology at Central Forensic Science Laboratory, Ministry of Home Affairs, Government of India.
So the person who is visible on the screen is Irving Sunshine. He's very famous toxicologist, and he said once that learning toxicology is very easy. It only takes 2 lessons to become an expert, and each lesson takes 10 years. So you can imagine that how much of expertise and how much of time it is required to to become an expert of forensic toxicology. And I have spent only 15 years in this field. So even I am also learning in this field. So just to begin with, what is toxicology or what is forensic toxicology? So we have to understand the analytical toxicology first. So analytical toxicology is basically, it deals with the screening, confirmation, identification, and quantification of xenobiotic compounds. So in analytical toxicology, we call drugs and poison as xenobiotic compounds because the compounds which are not present in our human body, they are not indigenous to our human body, and they enter from the outer environment to our body. That's why they are known as xenobiotics. So these analysis of these xenobiotics in biological samples is known as analytical toxicology, or some other samples also. So analytical toxicology can be further divided into 4 subgroups. First is clinical toxicology, then post-mortem toxicology, then comes forensic toxicology, and then environmental toxicology. So you can see from the definition that clinical toxicology, it deals with the samples of clinical origin like blood samples and urine samples and all other samples which are in biological origin, and they are ant-mortem in nature. When the victim is alive, then when you are analyzing some drugs and poisons in the samples of the victim when he is alive, then it is known as clinical toxicology. And these laboratories are basically attached with some forensic hospitals and forensic medicine departments where the poisoning cases are routinely encountered. Then comes post-mortem toxicology. So when the victim is dead, then the post-mortem or autopsy is performed of the dead body. Then this examination is known as post-mortem toxicology to ascertain whether there are some symptoms of poison or not. Then comes forensic toxicology. Now, when any legal angle is added to this investigation, then it is forensic toxicology. Forensic means legal. So it deals with the analysis, the analytical portion in clinical toxicology and forensic toxicology is almost 99% same. Only the samples differ because in forensic toxicology, you will be dealing with post-mortem samples. In clinical toxicology, you are dealing with ant-mortem samples. But the protocols and the analysis is almost same. Then another field is environmental toxicology, which deals with analysis of pollutants and toxicants in environmental samples. So we are not concerned with this field right now. Yeah. So all of us know. So I will, I read this slide very early, very rapidly. So what is forensic toxicology? It is the science of isolation, detection, identification, interpretation of drugs, poisons, and xenobiotics. So isolation, that means you have to extract your poison or drug. Then detection, then identification. So detection and identification are basically interchangeable terms. Then interpretation of drugs and poison in human body for the purpose of medical legal investigation. So this is the basically legal angle which is added in clinical toxicology. Matthew Orofila, he was a French toxicologist. He is considered the father of the modern toxicology, and he made first attempt to systematically study and categorize the poisons. Now, what is a poison? All of us know everything, every substance can be a poison. As the Paracelsus in 1500 said that all the substances are poisons, there is none which is not a poison. Only a right dose differentiate between a poison and a remedy. So you can see when you are taking only one aspirin, then it will be acting as a remedy. And when you are taking more than one, like 50 or 100 tablets of aspirin in one go, then it will be obviously a poison. So what is the difference? The difference is the dose. So where any substance which is capable of causing the illness or death of a living organism, when introduced or absorbed into the body, it will be known as a poison. Now coming to the classification of poisons, all of us we know that there are multiple type of classifications which are available in the textbook of forensic medicine toxicology. In 1848, there are scientist Taylor. He has classified the poisons into three category: irritant poisons, narcotic poisons, narcotico-irritant poison. Then the most recent classification, it also classifies poisons in three category: corrosive, irritant, and systematic. So these are the classification which are based on the symptoms of the poisons. Okay? Corrosive poisons, acid and alkali, sulfuric acid, sodium hydroxide. And irritant poison, they may be inorganic, they may be organic. Okay, they are vegetable poisons, animal poisons like snake venom also, they are also irritant. Then systemic poison, like they are systematically they are acting on a particular area or particular organ of the body. So basically they are somniferous, opium poison. So these are the classification which is available in any textbook of the forensic toxicology. But from the point of view of forensic toxicology, from the point of view of analytical toxicology, this is the classification which is very much helpful, and this is the classification which is prevailing throughout the globe in forensic toxicology laboratories. So these poisons are classified according to their extraction from biological samples. So basically, the poisons are classified into seven groups. Poisons are classified into seven groups. Group one is gas. So here you can say carbon monoxide, hydrogen sulfide, cyanide. They comes into gases groups because they are gases. Then volatile substance. Volatile substance basically volatile organic chemicals like methyl alcohol, ethyl alcohol, and other solvents. So and the most prevalent example is ethyl alcohol or methyl alcohol in this group. Then the group three is drugs. So drugs can also be classified. So drugs are basically organic. Obviously, drugs are organic. So they can be classified into three categories according to their extraction properties: basic, acidic, and neutral. So in basic acid category, all we know that benzodiazepines are the classical example. In acidic category, barbiturates and paracetamol. In neutral category, paracetamol and some other drugs are also the example, like valproic acid, mild acidic. Then comes metals. So metals are heavy metals: lead, arsenic, bismuth, etc. Then come pesticides. So pesticide is a different category of poison. Although it is a organic class, it is also organic, but they have different symptoms and they have different mode of action. That's why it is classified, and they have different extraction properties. Because drugs, you have to we will be discussing why drugs and pesticides are kept in different categories. So by the slides passes, you will be able to understand why this factor is there. Then comes anions, and then miscellaneous substances. Now, what is the role of analytical toxicologist? What analytical toxicologist or forensic toxicologist do in a laboratory? So basically, we have to detect, identify, and measure the unknown compound or any xenobiotic which is suspected to be a poison by which the death has occurred of a victim. So detection can be accomplished by basically by color test and thin layer chromatography. These are the classical examples of screening techniques. Then once you have you got to know that okay, some class of like barbiturate or benzodiazepine class of drug is present in the sample, then you will go for identification. So detection is basically, or color test or TLC are basically for not TLC, color test are basically for the identification of group of compound, not specifically what compound is present. So the identification basically deals with what compound or what drug or what xenobiotic is present from that particular group. For example, from color test, you will be able to identify that some benzodiazepine is present, but you will not be able to identify which benzodiazepines. By the technique of exact identification like GC mass, LC mass, you will be able to know exactly which benzodiazepine is present. This is no lorazepam, diazepam, nitrazepam, whatever it is. Then measurement. Measurement, it means the quantity or the amount of that particular drug which is present in your sample. So it can be done by calibration graphs, by analyzing standard substance, certified reference material. So we will also be discussing these all three aspects in analytical toxicology. Now, before moving further, we have to understand what are the nature of samples. which we are receiving in our laboratories and forensic laboratories. So am I audible to everyone? Please ping me with me. Am I audible?
Yes, you are.
Yes, yes, yes. Okay. So basically, in forensic toxicology laboratory, it is not necessary that we are receiving only post-mortem samples. We are also receiving ant-mortem samples. So ant-mortem samples are biofluid samples, biological samples, urine, blood, plasma, saliva, gastric levels, etc. And keratinous samples like hair and nail. In post-mortem samples, obviously all the visceral material we are receiving. Then visceral material means the vital organs of the body which are collected during the autopsy by a doctor, and they sent to us for examination. Then biofluid, all the biofluid like blood, urine, gastric levels which were applicable in ant-mortem. But here comes cerebrospinal fluid, bile and vitreous humor. They are the peculiar post-mortem biofluids. They cannot be collected ant-mortem. Then unconventional samples also they are being sent for in our laboratory for examination, like cream biscuits, tea, sweets, pharmaceutical tablets, capsules, ointment, water, vegetables. Sometimes, from criminal intent, some criminals, they can mix some drugs or any poison to these food materials, and when it is being eaten by victims, so sometimes police also sends these affected material or these food materials for our laboratory for analysis. Now what is generalized analytical workflow, what we do with a sample? So first of all, preliminary screening using color test, as we have discussed, it will give you what class of drug or class of poison is present. Then sample preparation. It is a very crucial parameter, and we will be discussing further why sample preparation is needed and why it is important. In sample preparation means you have to extract your poison or drug from the biological samples, for example, blood or tissue. So because you cannot directly subject any biological sample for analysis in any chromatographic or spectroscopic technique, you have to isolate or extract your drug or poison from the sample, then that is known as sample preparation. Then after sample preparation, detection and identification. So you can identify, to the some sort of some class, you can say that, okay, this OP or OC or carbamate is present by using thin layer chromatography. It is very classical technique in forensic chemistry. Then quantitative analysis by GCMS and HPLC. So according to my experience, GCMS is the gold standard technology, which is right now available in each and every forensic science laboratory in India and across the world. It has a very much advantage of a very good library, which is provided by the vendors, which is developed by NIST in USA under identical conditions. So there are lacks of compound, which are the spectra of compound which is stored in the library. And after analyzing the samples, you can unambiguously say that, okay, particular this drug is present in the sample. So whenever you are having GCMS with you, so there is no meaning of doing TLC or some other technique, because after sample preparation you have to do TLC. After sample preparation, the same samples can be analyzed by GCMS also. Now moving further, we will be discussing some nature of samples and what kind of samples we are analyzing and what information we can gather from these samples. So the first and foremost sample, the most prevalent sample in any ant-mortem or post-mortem case is blood sample. So in any living human, as an analyte concentration in blood are very closely related with their dose and biological effects. So beside blood, plasma and serum are also used for analysis of drugs. But please remember that plasma and serum is only available in cases of ant-mortem sample, because in post-mortem cases, when preservative is added, you will not be able to separate any plasma or serum from those blood. So in that case, whole blood you have to analyze. Then post-mortem toxicology. In post-mortem toxicology, blood is highly required for quantitative analysis. So this is a very, it's a very deep topic. You cannot quantify the drug, or you cannot exactly or very reliably say that, okay, this is the concentration of blood in stomach. This is the concentration of drug in stomach or tissue sample. But you can very certainly say that this is the concentration of drug in blood sample, because blood is very homogeneous in nature, and the distribution of any genobiotic compound in blood is very homogeneous in nature. while the distribution of any drug or xenobiotic or poison in tissue samples is non-homogeneous in nature. So you are not able to understand what portion of the tissue, what portion of the liver or stomach the doctor has sent, and you cannot certainly say that if the concentration of the poison in this portion which you are analyzing, it will extrapolate to the sample which is left in the body of the victim. So there is, this is the global practice. This whenever the concentration of any xenobiotic or poison is expressed, it is expressed in blood sample only, not in tissue samples. In tissue samples, we will do only qualitative analysis. Now coming to next to that, blood and relative samples such as plasma, serum are highly complex, obviously, and they require deproteinization before extraction of xenobiotics. So whenever a person consumes any drug or any poison, so when the drug go through a process of adsorption, distribution, metabolism, excretion, that is basic pharmacokinetics. So when the drug is absorbed into the body, it is absorbed by the help of blood, and uh, in the blood there are some proteins. There are a number of proteins. So drug, make a bond with these proteins. This is known as drug protein complex. So that drug protein complex, it interferes in the isolation of the drug in any organic solvent. So in that case, you have to break that drug protein complex, and that drug protein complex will be broken by some some chemicals and solvents. So without breaking that drug protein complex, it is very difficult to extract or isolate your target compound. Now coming to urine sample. So urine sample, so it is also very important sample in drug screening. And that you collection of urine is non-invasive in comparison to blood samples. But the problem is that in most of the post-mortem cases, urine sample is not available. In ant-mortem cases, urine sample is available. And it is very relatively simple matrix, and it comprises 99% of water. So the problem of deproteinization or the problem of drug protein complex which is there in blood sample, that is not prevalent in urine sample because it is comprising 99% of water. And it is also an advantage for spot test analysis. Why? You just take the urine sample and apply some spot test for the qualitative or some for the detection of any class of drug. So urine is very important, very useful. However, in forensic postmortem toxicology, urine is available only 50% of deaths, as bladder usually voids during the dying process. So usually in our laboratory, we do not receive any urine samples in 99.9% cases in postmortem uh, cases. Then comes stomach and its content. So, stomach, it is very much useful for the toxicological screening of drugs and poisons, and it is very much useful in cases of oral overdose. So mostly whenever any victim commits suicide uh, by consuming any poison, the route of administration is oral by ingestion. So the poison directly gets into the stomach, and from there the poison will act. So in that case, the stomach becomes very important because some unabsorbed poison, some unabsorbed tablets, suppose somebody has consumed 100 tablets of paracetamol. So uh, after death, some undissolved tablet will be there in the stomach. So they will be visually identify. You can visually identify that there are some tablets are present in the stomach. So this is very much useful for screening purpose also. As I have written, that unabsorbed tablets or capsules may also be detected, and the drugs or the xenobiotics, they are detected in parent form in the stomachs. For example, if somebody has consumed cypermethrin, that is the pyrethroid pesticide, so it will be detected in stomach in the form of pyrethroid. It will not be detected in the form of 3-phenoxybenzoic acid, which is a metabolite of pyrethroid. So when you were analyzing liver sample, as we will be discussing in further slides, liver samples, they are very much available with metabolites. So stomach is very useful in toxicological screening of xenobiotics. Now coming to liver, as I've said that it is a primary solid tissue used in postmortem toxicology for the analysis of drugs and poisons, and it is the main metabolic organ of the body. So whatever the drugs or pesticides, they will be which are detected, being detected in the stomach, the metabolite, there is a probability that you can detect metabolite of these drugs and poisons in liver samples. And the concentration of drug in liver is relatively stable after death, because after death, this is very compact organ and there are very less chances of post-mortem redistribution. The concentration of drug or poison actually differs after post-mortem, after death of a person, because there is a phenomenon known as post-mortem distribution. Post-mortem distribution happens basically, you have must learn that there are two kind of diffusion: active diffusion and passive diffusion. So whenever the concentration of any analyte is greater in the portion A and very low in the portion B, then the drug will be automatically migrate from higher concentration to lower concentration. So this is known as passive diffusion, but it is not in the case of liver. Then it is relatively larger database in literature is available for liver drug concentration compared to other tissue. Useful specimen when other fluids are limited, for example, in baby infant cases, because in baby infant cases we are also receiving, like 1 year baby, 2 year baby, or very new fetus. In that cases, this is very important organ, because some other organ or blood and urine samples are not available in those cases. Then comes saliva. Then comes saliva or oral fluid. So saliva is also a non-invasive sample, like can be done without violating. For many drugs, only free fraction is physiologically active. Therefore, saliva can be a better indicator to the state of intoxication. Then hair and nails. So these are basically, these can be collected post-mortem as well as end-mortem samples. And hair and nails are basically the calendar of exposure or calendar of chronic exposure of a person to a particular drug. So you can get some retrospective information of drug abuse by analyzing hair and nail samples. So they are basically, a person is consuming, suppose he is consuming heroin or any drug for a period of time, then that drug will from the blood stream, it will go to the hair shaft, and when the process of keratinization of the hair or the keratinization of the nail will begin, then the drug will trapped between the keratin protein of the drug and nail and hair. So samples or these biological tissue, you cannot sit in here as a tissue. During the keratinization process of these hair and nail samples, the drug is entrapped or drug is get trapped in the keratin protein. So when as the time passes, the drug trapped in the hair sample. So it is being a calendar of exposure, and it is suitable for retrospective analysis of drug of abuse. So various drugs of abuse like amphetamine, cannabinoids, benzodiazepine, trace elements like arsenic and doping substance, they can be detected in hair and nails. And you can ascertain, there are some databases also available where you can ascertain that if this much of concentration of particular drug in hair sample is present, then you can retrospectively you can say that the person is consuming this particular drug for this period of time. It's a very unique topic of research also. Now we will be discussing some practical aspects of forensic toxicology. Now I'm taking you in the laboratory of a forensic toxicology, where how the samples are received, how we have to open the samples, and what are the crucial information which we have to record during the opening of the samples or during the receiving of the samples. So you can see here is a unopened parcel. The parcels are look like that they are generally they are being wrapped or sealed with the seal of forensic medicine expert, and they are sealed in a white cloth cover. And whenever you are receiving any sample in a toxicology division, then you have to verify some facts. First is document verification. then parcel verification, and you have to register some anomalies if there are some anomalies are there. So first of all, you have to see the forwarding letter which is being forwarded by the legal agencies to you. So we have to know what are the DDR, forwarding letter number, what is the case history, MLR and PMR. In case of ant-mortem sample, it would be an MLR, and post-mortem sample, it would be an PMR. Then sample seal, you have to, this is very crucial in maintaining the chain of custody. You have to, match the sample seal which is available on this parcel with the sample seal which is supplied by the forwarding authority. Then the identity of the messenger has also be ascertained. The messenger who is bringing the case to you, then the name of that messenger should be recorded in the forwarding letter by the legal agency. Then road certificate, nobody can, these are legal, and these are legal parcels. Nobody can carry these parcels without permission on the road. So there is a road certificate which is given by the legal authorities to that particular messenger to carry these parcels to the laboratory only. Suppose a messenger is carrying to CFSL Chandigarh, then the road certificate will be for CFSL Chandigarh only. He cannot carry this parcel to any other laboratory. If he is carrying this particle to any other parcel to any other laboratory, then he has to get a new road certificate. Then statement of legal use. In case of post-mortem forensic toxicology, the statement of legal use is very important, because what was the situation the victim was going through at the time of committing suicide, or at the time of at the time of death, or whether he has been admitted into the hospital, for how much time he has been admitted to the hospital, whatever the circumstantial evidence, like uh, any medicine is present beside the side of or near the victim, whatever the situation that is prevailing during the crime scene, that is recorded in the statement of legal use. So this is very much important. It is also important because it will give you some idea in which direction you have to analyze the cases. Suppose sometimes they say that the victim has some vomiting episodes. The victim had very large amount of vomiting. So in that case, you will go for obviously phosphide. You will go for pesticide poisoning. So these are very crucial information which you have to, before opening the case, you have to know, because toxicology, it is very vast subject. If you are not having some clues or hints, then you will not be able to solve the case. But each and every case will take at least 6 months in that case if you are not having any information. Now, parcel verification. So obviously the sample seal has to be verified, the number of parcel and exhibits. So number of exhibit will be verified after opening the parcel. The name of deceased in the case of PMR number, in the PMR number, the name of deceased which is mentioned on the PMR number, it should be mentioned on the parcel also. Because in toxicology, the exhibits are basically biological samples. You cannot mark the biological samples by using a marker. You have to mention the name on the parcel only. In other disciplines of forensic science, like in ballistics division, in cyber division, you can directly mark the exhibit. But in case of forensic toxicology, you cannot directly mark the exhibit because these are biological samples. So name of accused victims in case of MLR, check for any leakage of the parcel, and this is very crucial. In our scenario, in Indian scenario, some parcel becomes they the fluid in which they are being preserved, it is being leaked. So if the fluid is leaked, then we have to return the parcel, and it is very common in our country. So these are the some points which we have to keep in mind. Then register or intimate if any discrepancy is noted during the case acceptance. If you are noting any discrepancy, like the number of the parcel is different from the parcel mentioned on the forwarding letter, then you just note the discrepancy on the receiving which you are giving to the messenger. Now, this is the most important question, that is, after acceptance of the parcel, this should be immediately kept under refrigerated conditions, because all the samples are biological samples, and biological samples start deteriorating or decomposing at room temperature. So this is very crucial. Then opening of the case. Now we have received the case. Now we are going to open the case. So what are the things we have to keep in mind? First, always photograph the entire process. So you have to start the videography or photography by keeping the parcel on the table in unopened condition, Don't mark the parcel, take a photograph, then mark the parcel, then take a photograph. Then cross-check the details mentioned in the forwarding note from the legal agency with those on the parcel and exhibits, whether they are matching or not matching. Then immediately fill down the case opening sheet. There is a case opening sheet. If you are, if you are delaying this process, then you will be losing some information, because sometimes what happens, we are being busy in some other casework or some other assignments. Then if we are not noting the discrepancies or whatever the discrepancies is there right at the time of opening, then you will be losing that information. There are chances that you can forget, because there are no single case. We are analyzing more than 50 cases per month, more than 60 cases per month. So this is the practice which should be considered. Record every minute detail of exhibit in case of opening, like box, jar, vial, injection, markings, obliterations. If you are getting, sometimes the police person, they are sending some tablets or pharmaceutical samples, so they are obliterating the details. So if the details are obliterated, then note them in your case opening sheet. Then note down any discrepancy in case of exhibit with those mentioned in forwarding note. Check for weight quantity of the sample. It is very crucial, because whenever you are giving the evidence, they will ask you what was the sample amount of the sample you have received, what amount you have used consumed for the analysis, and what amount was the remnant. Then check for specific order or color. Now, so how does a parcel looks like? So you can see this is a parcel before opening and after opening. So before opening, you can see there are some seals, and the parcel is being wrapped in a white cloth parcel, and it is being sealed by legal agencies. Then this is the after opening. You can see there are 3 jars, plastic jars, and there is some information that is not visible. So the information is about the what is the name of the victim, what is the PMR number, and what is the sample of the what is the sample or visceral organ which has been collected from the dead body of the victim. So it is being affixed on a slip on the jar, and it has to be verified with the post-mortem report also. Now, so this is some administrative procedure I want to tell you, because future you will be working in forensic science laboratories, so it is good to have some idea. Now, commonly encountered cases of poisoning, because by going with textbook, there are a number of poison, but what are the common poison which we are encountering? So first of all, they are being in the order of priority. First is ethyl alcohol, whether it be a case of antmortem or postmortem, then phosphite poisoning, then drug overdose, pesticide poisoning, carbon monoxide, cyanide, and snake bite poisoning. Snake bite poisoning is very rare, but it is still being there. So we will be discussing ethyl alcohol, phosphite, drug overdose, pesticide, and carbon monoxide poisoning, how to analyze. And we will also discussing some real case examples for these classes. Now, coming to the sample preparation, as if you remember the slide of analytical workflow, where I have told you that sample preparation is very crucial. Why? Because you have to isolate your poison from the sample. Any sample in biological origin that cannot be directly subjected for analysis, you have to isolate the poison. That is known as extraction. So there are 5 common classes, as we have discussed, from extraction properties. One is gaseous. So the classical method of extraction is diffusion, obviously micro diffusion. Then volatile. For volatile compounds like ethanol and methanol, the distillation is a classical method. For organic non-volatile means drugs. So solvent extraction is there, liquid extraction, which is known as. Then metallic. So you have must read about dry acing and digestion methods. Then anions. Then so dialysis comes for anions. But remember, these are the classical methods, and these are still being taught in textbook of your forensic curriculum. But some of the method we will be discussing, like some of the method are totally obsolete, like distillation. By the invention of technology like headspace gas chromatography, headspace GCMS, distillation is obsolete. Solvent extraction is there. Okay, and then dialysis, by the invention of ion chromatography, we are not doing dialysis. We are not doing diffusion for carbon monoxide, because UV spectroscopy is there. Now, coming to preliminary analysis. So you can understand that we have received the sample. We know what are the common poisoning in our area. So we will go for some preliminary analysis. So if we have received, if there are that is a case of ant-mortem or post-mortem, if you have received some urine samples, so you can do some, color test with that urine sample, just to confirm or just to eliminate the common poisoning, like Trinder test for salicylates, because aspirin, that is acetyl salicylic acid, and some other salicylates, they are very common. They are very commonly consumed, and sometimes, when the people in depression, they consume number of tablets for committing suicide. So these can be easily detected. The class of the drug can be easily detected by using these spot tests. Then come cresol ammonia test. It is very common and very specific test for paracetamol. And then phenothiazines, for phenothiazines you can use FPN test. Then for Fujiwara test you can use for chlorinated compounds. So all these tests, the details of all these tests which I'm talking here, you can easily get in any textbook. And if you are not able to get the details of these tests, just contact me. They are available in Clark's Analysis of Drugs and Poisons. Then some physical analysis you have to do, like you have to observe for the tablet residue in stomach content. If you are if it is a case of post-mortem, then you will be getting some stomach content. So observe that stomach content, some food particles will be there. And if the person has consumed some large amount of tablets, okay, so some unabsorbed tablet will be there, like paracetamol or benzodiazepine. If a person has consumed, organophosphorus pesticide, for example, dichlorobos and chlorpyrifos, so they are commercially, they are, when you will see, they are being used in agriculture practice. So they are green in color because their vehicle is green. Now, carbon monoxide, as of all of us, we know that, there are some cases of fires and emissions from improperly maintained ventilated heating systems. In those cases, the carbon monoxide poisoning happens, and basically it is a poisoning, accidental poisoning kind of cases. And it can also be detected in dichloromethane poisoning, because carbon monoxide, it is a metabolite of dichloromethane. And all of us, we know that carbon monoxide is 200 to 300 times carbon monoxide have a affinity 200 to 300 times greater than oxygen for hemoglobin. So it will form carboxyhemoglobin, and it will be the fact that we are exploiting for detection of carbon monoxide in blood. So here you can see the UV visible spectra. Is it visible to everyone?
Yes, sir.
Yes. So you can see there are three spectra, A, B, and C. Okay. On the x-axis we have wavelength, and on the y-axis we have absorbance. So it is the B sample, the black line, darker black line. It is a negative control. Negative control means it is a normal blood which is not being poisoned with carbon monoxide. So you can see this is the absorbance of hemoglobin. But in case of sample and positive control, you can see twin peaks. It is the absorbance of carboxyhemoglobin. Okay. So when the blood sample, it is being treated with when the blood sample is being treated with sodium dithionate, it is a reducing agent. So when you treat the blood sample, then you will get this kind of your carboxyhemoglobin. It is being reduced to reduced to A and C. Okay, so it will be reduced to carboxyhemoglobin. Okay, then reduced hemoglobin. So B is the reduced hemoglobin, and A is the reduced carboxyhemoglobin. You can see the positive control or the sample. These two are reduced carboxyhemoglobin, and B, that is negative control, it is the reduced hemoglobin. So in case of negative samples, you will get a simple peak. But in case of carbon monoxide poisoning, you will get twin peaks by UV spectroscopy. Now coming to the most prevalent and most common poisoning, that is alcohol poisoning. So previously it was done by Kozelka-Hein method. If you have, I think most of the students in their textbook have learned about Kozelka-Hein method. That was invented by Kozelka-Hein in 1943. But it is very obsolete method, and you will not be able to purchase the glasswares which are being used in Kozelka-Hein methods nowadays. So classical method was Kozelka-Hein. The modern method of analysis of alcohol in blood is headspace gas chromatography. So we will be discussing some some protocols also. So just take a blood sample, 1 ml of blood sample, and dilute it with ultra pure water or distilled water, and just put your sample in the headspace sampler. Headspace sampler will heat the sample at 70 degrees centigrade, whatever the settings you will get input in the instrument, for 30 minutes. For a particular time period, it will heat the sample. And since alcohol, methyl alcohol, chloroform, all the volatile components, they are volatile in nature. Due to the heat, they will come into the head space of the vial. Okay, and that head space, or that the space above the liquid sample in the vial, that will be sucked by the auto sampler, and it will be injected into your gas chromatography. And that gas chromatography, that is coupled with flame ionization detector, that will be able to detect the ethyl alcohol. It will be able to separate ethyl alcohol from any other volatile poison also. So these are the chromatograms which you will get after analyzing blood alcohol samples. The above chromatogram, that is the chromatogram of standard ethyl alcohol which has been spiked in a blood sample at 100 mg% concentration. So under the some under defined conditions, your ethyl alcohol will elute at 8.71 minutes. So these are the chromatograms of our laboratory. Some other laboratory may have some different chromatogram. They may have some different instrumental conditions. So the ethyl alcohol may elute at some different time. So it is not fixed for each and every laboratory. Then the below chromatogram, it is the chromatograph unknown blood. So you can see the standard peak is at 8.71 minute, and the unknown blood, you have got a peak of a compound of alcohol at 8.67 minute. So the deviation in the RT, okay, the deviation in the retention time is which is allowed as per the international guidelines, that is plus minus 2%. So the retention time between 8.54 to 8.34 in the identical circumstances in an unknown sample, it will be considered as a peak of ethyl alcohol. Got it? So the preliminary test which we have used for this sample for detection of ethyl alcohol is dichromate test. That is the mixture of potassium dichromate and sulfuric acid. So you can use the micro diffusion test, and when the green color appears, it is indicative of ethyl alcohol poisoning. Now coming to the next slide, how to quantify the ethyl alcohol, because quantification of ethyl alcohol, it is being asked in each and every case, and there are some statutory limits for in each and every country for the consumption of for the alcohol level in the blood samples. In India, we have a 30 mg% level, that is the cutoff level, 30 mg%. If it is below 30 mg%, then it is okay. If it is more than 30 mg%, then it will be a problem. So in that case, we have to quantify the ethyl alcohol in blood samples. Okay, that is known as blood alcohol concentration. So how to quantify, or how to find out the level of ethyl alcohol in blood sample? So what you do, you will plot a calibration graph. If you can see, you will plot a calibration graph where you will run different concentration of sample, 10, 50, 100, 200, 300, 400 mg, and you will record the area, like this is the area of 10 mg, then 8 for 50 mg, 100 mg, 200 mg, and you will simply plot a calibration graph, that is linear regression curve, against where you will take concentration on x-axis and peak area on y-axis. And you can see there is a very good correlation. The line is very much linear, and you have got a very good correlation coefficient, that is 0.998 r square. So it should be always greater than 0.990. So it is 0.998, and you got an equation that is known as y is equal to mx plus c, where y is peak area and x is concentration. So this x is concentration. Now these are the calculations. You can see below I have put some calculations. This is the x is for concentration. For unnamed samples, you have to determine the x is concentration of alcohol, y is 0.5. For example, the area of alcohol in blood sample, in unknown sample, is 0.5. Then c is the intercept, that is minus 0.949. This is, and m is the slope of the calibration curve, that is 1.195. And dilution factor, we have taken 1 ml of blood, then diluted it to up to 5 ml of with ultra pure water, so your dilution factor will be 5. So just put the values in the equation. You got a value of y, you got value of m, you got value of c. You have just to determine the value of x, and it will be like calculated value will be like 7.43. But since we have diluted the sample for 5 times, we have to apply a dilution factor also. So it will be, after multiplying with 5, the final concentration will be 37.513. That means the amount of alcohol which is present in the blood sample of unknown nature is 37.515 mg percent, which is very much higher from statutory limit, that is 30 mg percent. Now, these are the common techniques: spectroscopy and chromatography. These are the techniques which we are using for identification of drugs and for quantification of drugs. So I'm not going very deep into these techniques. Now, what is the need of the sample preparation? As we have discussed, why we have to prepare a sample, why we have to isolate the sample. So as I have told you earlier, the direct handling of biological sample is not possible by any analytical instrument. You cannot directly inject blood into HPLC. You cannot directly inject blood into or urine into GC mass. You have to extract your compound. So biological samples, why? Because biological samples are very complex in nature and they contain number of endogenous substances. They contain protein, they contain fats. So those protein and indigenous substance will interfere with your xenobiotics. That means the compound which you want to extract. Then goal of the sample preparation is to provide a homogeneous sample that is free from any interferences. For the accurate and reliable analysis of xenobiotics, we have to extract them from biological samples by various techniques, and these techniques are generally known as liquid-liquid extraction or solvent-solvent extraction. During the sample preparation, compounds are purified. Okay, they have been isolated in organic solvent, then concentrated. You have after isolation, you will concentrate, you will evaporate the sample and supplied in a medium compatible with analytical instruments. Suppose you want to analyze the sample from HPLC, then you will dissolve the extracted compound in methanol or water. If you want to analyze the extract with GC mass, then you will dissolve in hexane or ethyl acetate or methanol. So it depends on the analytical instrument. Then sample preparation is the most critical step in analysis of xenobiotics from biological sample. So basic steps of sample preparation for drug analysis. We have discussed volatile compound, we have discussed gaseous compound. Now we are coming to drug analysis. So we will take the example of, for example, benzodiazepine drug. So first of all, first and foremost, whether you are taking blood sample or tissue sample, first step is protein precipitation. As a goes into the body or a poison goes into the body, it interacts with the protein which is available in vital organs and blood sample. Then you have to break the protein and drug complex. Why we have to break that complex? Because protein are very high molecular weight compound. They are not easy, they are not extractable in organic solvent, and you want to extract your compound in organic solvent, for example hexane and chloroform. So that's why you have to precipitate the protein. In case of tissue sample, you have to homogenize also, because suppose this is the stomach sample and you are taking this much of portion for extraction, but you know the compound may be present here also. The compound may be present in higher concentration in this portion, and the portion which you are taking, the compound may be present in low concentration. So what you have to homogenize the sample. That means you have to make a slurry of this whole tissue sample, and so what will happen? The compound will be evenly distributed throughout the sample. So whatever the portion you are taking, and the compound will be present at even concentration. Then digestion is necessary. Why? Just to, in case of tissue sample, digestion is necessary to precipitate the protein again. Now after protein precipitation, what happened? You have a protein particles in the blood sample or tissue sample, and you have tissue and blood particles. So you have to centrifuge your sample. By the mean of centrifuge, the higher particles, they will be sedimented in the conical bottom, or you have to filter your sample. So you want a liquid sample, completely aqueous sample. Then you have to adjust the pH. pH is very much crucial factor. If you want to extract basic drug, then the pH of the sample should be basic alkaline, that is from 8 to 12. Then if you want to extract acidic drug, for example, you want to extract barbiturates, then the pH of the sample should be around 3 to 5. So it is very crucial. Why it is crucial? Because the compounds are present, the compounds which you are extracting in organic solvent, they should be present in their neutral form. They should not be present in their ionic form, because the compounds got ionized in water sample and aqueous sample. Compounds got ionized, they form cation and anions. In order to get their molecular form, you have to adjust the sample around their pKa value. Okay, so basically the basic compounds which are having pKa value more than 9, so you have to adjust the pH of the sample around 10. If the compound is having pKa value around 5 or 3, then you have to adjust the compound pH of the sample around 5. So it will be decided according to the nature of the compound which you are extracting. Okay. So this is the crucial factor, pH. If you are not adjusting the pH, that means you are going to lose your compound in your extract. Then finally comes extraction. So extraction can be performed by classical method, that is liquid extraction and solid phase extraction, or by some modern method. These are known as microextraction, which we will discuss. And then after the extraction, we will go for analysis by GCMS or some other techniques. Now, what are the factors which affect the extraction of analyte? The session is going on now.
Yes, sir.
Okay, so what are the factors which are affecting the extraction of analyte? Obviously, that different water immiscible solvent. The first is solubility. Solubility of your compound. Solubility, for example, you want to extract nitrazepam. So solubility of nitrazepam in the organic solvent which you are taking for extraction. If the nitrazepam is not soluble, then there is no meaning of taking that solvent. Then pH, obviously, nitrazepam is an alkaline drug. So you have to adjust the pH of the sample to basic, towards basic. How you will adjust? Just put some 1 molar sodium hydroxide in the sample and measure the pH. The pH will be adjusted. Then ratio of the solvent and the sample. How much of the solvent, for example, chloroform, how much of the chloroform you have to take for 10 ml of the sample? Typically 1:2. If the sample is 10 ml, then chloroform should be 20 ml. Then ionic strength. It is also very important factor. You have to adjust the ionic strength. So what is ionic strength? Ionic strength is nothing but it is the strength of ions which are, for example, you have added sodium chloride in your sample. What happens? I would like to throw some light on this factor. Suppose this is a water sample and it is containing your nitrazepam. But what happens in aqueous sample, your nitrazepam, nitrazepam, molecule of nitrazepam is surrounded by number of molecules of water. Okay, it is not free. It is not freely moving. So in order to get, it is being trapped in water molecules. In order to detrap it, or in order to extract, or in order to, make it free from the water molecules, you will add some sodium chloride into your water samples. What happens? Sodium chloride, it will dissociate into sodium positive and chloride negative. So the ionic strength of the sample will increase. And the water molecules which were initially surrounding your nitrazepam, they will be surrounding your sodium and chloride, sodium ion and chloride ion. Sodium ion will be surrounded by OH negative and chloride ion will be surrounded by H negative. So what happens? It will free your drug. It will free your nitrazepam so that it can be easily extracted in your chloroform or organic solvent. Then extraction time. It is very much important. Extraction time is very much important in case of in order to achieve equilibrium. You must be aware of what is the equilibrium. Equilibrium is nothing but the amount of the solvent. For example, this is your water and this is your chloroform. So the amount of analyte, okay, this is the dots are nitrazepam. The amount of nitrazepam which is present, the ratio of the nitrazepam to the organic or chloroform with water. Okay, so this is the equilibrium. At equilibrium condition, the amount of the nitrazepam which is present in water will be equal to the amount of the nitrazepam which is present in chloroform. So in each and every extraction, you have to go for the equilibrium condition. Got it? So equilibrium is very much important. If equilibrium is not established, then that means your recovery will be very low. And if recovery are low, then you will not be able to isolate or not be able to recover all of the nitrazepam from your sample. Now coming to liquid extraction, it is very much prevalent, mostly used extraction method in most of the forensic science laboratories. So as all of us we know, we have to homogenize and digest the sample, then protein precipitation, pH adjustment, and extraction. So you must have seen in your laboratories this kind of glassware. This is known as separating funnel. It is called a separating funnel, and it is oval shaped in nature. It is a cork or a opening at the top, and at the bottom it is fitted with a funnel tap. So what happens, you have took the higher density liquid. Okay, higher density liquid means water means your sample, okay, your filtered sample. So you have took water at the bottom, and you have added some low density liquid. So which solvent is low density from water? Hexane. Okay, for example, you are extracting a pesticide, so you have added a hexane. After adding your sample into the separating funnel, you have added hexane. So hexane, what happens? Hexane is having lower density than water, then it will obviously it will settle above the water, and the water will be below the hexane. So after extraction, whenever you are mixing these both the organic, since they are immiscible with each other, you will agitate this separating funnel for a number of times, sorry, for 50 or 100 times. So at that time, equilibrium will establish, and your nitrazepam or pesticide, it will come into the hexane layer. Okay, pesticide will come into the hexane layer, and after that, after extraction, you will allow this separating funnel to stand for 5 minutes or 10 minutes, and automatically the both layer will separate it from each other. The higher density water will be settled at bottom, and higher density lower density hexane will settle at above the water. So by by moving this funnel tap, you can take the water and hexane separately in your beakers and flasks. Okay, so this is practically, this is the liquid separating funnel. You can see this is your visceral material, aqueous solution, and this is your hexane. Okay, so what are the drawbacks of LLE? We are using LLE in our routine practice, but there are some drawbacks also. It consumes large volume of toxic organic solvents. For a single extraction, you will require more than 100 to 300 ml of organic solvent, because you have to extract the sample 3 times in LLE. And organic solvents are are hazardous to human health and environment, and the procedure is very laborious and expensive too, as the organic solvents are very costly in nature. It is time consuming. Uh, the extraction of a single exhibit will be completed around 1 to 2 hours. Okay, then multiple extraction are required. Not a single extraction will be sufficient, because 80% of the analyte is extracted in a single extraction. Then you will to repeat the extraction for 1, 2, and 3 times. Then you will combine. So for a single exhibit, you will consume around 500 ml of the organic solvent, and 2 hours of the extraction time. Then it is suffering from low recoveries, and emulsion formation is there, because chloroform, by the means of rigorous shaking, the chloroform or hexing, they form emulsion in water, that is oil in water emulsion. Then additional pre-concentration step is required. So you have used 100 and 100 for 3 times. So the total amount of the solvent is around 300 ml. So now you see this amount, this 300 ml is very much large amount. Your compound, although it is extracted, it will be very position in a very dilute position. You will not be able to detect from any analytical instrument. So you have to evaporate this hexane or chloroform up to 1 ml, 1 ml or 2 ml. Okay, so this is known as the pre-concentration. Now we are going to discuss generalized extraction procedure of drug from blood sample. So take 1 ml of blood and deproteinize with any polar solvent. Whenever you will add equal amount of methanol or acetonitrile, you will see that the protein of the blood is deproteinized. There are some particles of the protein which will be floating in the sample. So you will allow this sample to centrifuge at around 5000 rpm for 5 minutes or 10 minutes. Then you will get a clear supernatant, and that supernatant is taken in a separate vial, and it is diluted with buffer. If you are extracting acidic drug, then you will add acidic buffer. If you are extracting basic drug, then you will add basic buffer. Then again now this is the process of extraction. Okay, so you will agitate this supernatant, that is your liquid blood sample, with chloroform or chlorobutane, and you have to extract 2 to 3 times, then collect supernatant, evaporate, like I've told previously, and then it is ready for analysis. You can analyze it by either by TLC, by GC, or HPLC, or GCMS, whatever the technique you want to use, you can use, but the protocol will be same. Another technique which is being used is solid phase extraction technique. So solid phase extraction, you must have read in your textbook. It is basically it is like a column chromatography, but it is a miniaturized column chromatography. In column chromatography, you got a very large column around around 1 to 2 feet, and in that column you pack this column by any adsorbent, for example silica, and then you pass your sample, then collect the element in a beaker, and you pass again with different polarity solvents. So it is like that. SP is like that, but it has basically 4 steps. Here you can see it is a syringe like structure, and here this is the adsorbent. For example, this is C18. It is a non-polar adsorbent. Initially you have to wash or condition this adsorbent. So washing is basically done by any organic solvent. Then loading means whatever the sample in your liquid condition, for example deproteinized blood or urine, you can use urine directly. Load your sample, pass your sample. So what happens, these are the analyte, these dots and triangles, these are the analyte. For example nitrazepam, diazepam, these are the analyte present in your sample. They will get adsorbed on this C18 polymeric phase, and it is selective adsorption. You can see that circular compound. Suppose if this is non-polar, since C18 non-polar or mid-polar, so the polar drugs will not get absorbed. Only non-polar and mid-polar drugs will get absorbed. Then washing means since your compounds are getting got adsorbed on this stationary phase, you will elute those compound by selecting any appropriate organic solvent of appropriate polarity. Since it is C18, so you can use ethyl acetate or hexane, and you can get your adsorbed compound eluted in your hexane. Washing, sorry, this is washing. That means again you will wash it. So there are some, if there are some unwanted drugs or unwanted compound, endogenous compound are adsorbed, they will get dissolved, and after that you will elute your target analyte by any organic solvent of appropriate polarity. And this is the, for example, this is ethyl acetate or methanol portion, and you can analyze it by GC or GCMS or HPLC. Now, since time is passing, we will discuss some case studies. So first case we will discussing about paracetamol poisoning. Very interesting case. You will learn a lot of things. So this is basically a brief case study. What happened? A deceased consumed alcohol and suffered from several severe headache. Well, one person who has consumed alcohol, he has suffered from severe headache, and after consumption of that alcohol, he has lost his consciousness, and he has ingested some large amount of unknown medicine. Okay, after some time he started stomachache, blood stain, vomiting, bleeding from both nostrils, became unconscious and fell on floor. He was immediately taken to hospital, and he is declared brought dead. The autopsy of the blood, stomach, and liver samples were sent for analysis in our laboratory. So what we did, preliminary screening, as we have seen in the slides. So if you remember that I told that the statement of legal leads is very important in order to get the direction of the investigation. In which in direction you have to investigate, you start your analysis. So we have, we got this information from the legal leads statement, their relatives statement, that he was suffering from headache and he has consumed some unknown medicine. So we have applied a simple positive confirmation test for paracetamol, that is cresol ammonia test. It gives very, navy blue color, you can see, and it was positive. It was very much positive for paracetamol. Then what? It is positive for paracetamol. So this is the first confirmation. Then we have extracted the samples, blood sample and stomach sample for neutral poisons, and the protocol I have already shown to you. and we have applied that extract on TLC plate, and we got applied the standard of paracetamol. This is standard, and this is small intestine, this is liver, spleen, kidney, this is stomach, and this is stomach. You can see that the RF, or the spot which we are getting for stomach and small intestine, liver, spleen, kidney, and this spot, they are very much in line to each other. That means TLC also confirmed that okay, the RF of the sample is matching with the paracetamol. Then what, we the same samples we have injected into GCMS. So GCMS is a technique for unambiguous identification, because it has a library of lakhs of compound. So when we have injected the sample into GCMS, this is standard paracetamol, this is exhibit. You can see the overlapping peaks of paracetamol with standard. Okay, so in exhibit we got the paracetamol positive, and it got confirmed by matching the retention time with standard paracetamol. So this work has been published in journal Separation Science Plus, which is a journal of Village, a very good journal, a Scopus Index journal, and it has been published in 2020. Now coming to atropine poisoning, it is 2, not 1. Coming to atropine poisoning, okay. So atropine, Atropa belladonna, it is a very poisonous plant. So this is the case history, and this case has been recently analyzed by me. It's been only 1 year, I think. So it is a case from Arunachal Pradesh. 4 friends had a party in a jungle in Arunachal Pradesh. One friend had died just after eating the meal. Am I audible to all the students?
Yes, sir.
Okay. So remaining 3 friends concealed this fact. Okay, there were 4 friends. They had a party in a jungle, and they had some dinner or kind of meal, and one friend died, and remaining 3 friends concealed that fact. Police recovered body after 3 days, and autopsy was performed. The sample were analyzed by GCMS after LLE. So what are the results? I'm going to show you. So this is after extraction. The extraction protocol will remain same. For blood, you have to deproteinize the blood. Then you have to extract the sample with any organic solvent, then evaporation and reconstitution and analysis. So this is the whole total ion chromatogram. This is the total ion chromatogram which we have got for blood sample of the victim. When you will not get any information. You see the chromatogram very carefully. There are some peaks. These are the peaks of fatty acids. Okay, these are the peaks of fats. So the bloods are very much plentiful in fatty acids. So these fatty acids are also gets co-extracted with your compound. So there is no information. But when you zoom that chromatogram, there is some small peak is there, which is which is got normalized, and which has been missing in the forest of this peak. That is the atropine as 14.035 minutes. How we have confirmed that this is an atropine? We have confirmed it by matching the spectra with library. So this is the protocol for extraction of atropine from blood sample. Again, we have taken 1 ml of blood sample, then we have deproteined with methanol, then added a buffer solution, then we have agitated with chlorobutane. Organic layer was collected, and evaporation and reconstituted. Full scan TIC of stomach. This is the spectra of stomach. GCMS spectra of stomach. In stomach, it is very much prominent. You can see in blood it was very dull peak, but in stomach it is very much prominent. It is standing between these 2 fatty acid peak. So it is the atropine at 14.036 minutes. So this is the 142 is base peak of the atropine. If you are studying mass spectrometry, there is a base peak. Base peak is basically the most abundant fragment in the fragmentation pattern of any compound. This is the library match of the stomach and blood sample. So this is your unknown compound, which is having 124 ion MYZ, and this is your match with library, which is also having 124, and this is the library match. This is the structure of the atropine, which is shown by the library. It has been confirmed. This is written atropine, its molecular weight, each and everything is being confirmed unambiguously by the library. Now this is the atropine standard. After getting confirmed by the library, we have also run the standard pure atropine, and we have also got the retention time of pure standard of atropine at 14 minutes. And we also got the retention time of atropine in samples at 40 minutes. So this is again third confirmation. Confirmation by library and confirmation by mass spectra and confirmation by retention time, matching the retention time with your pure standard compound. This is very unique case. This I have recently, in this month only I have reported this case. Spiked food samples and blood sample. What happened? This is the case study. A maid had mixed some unknown medicine in the breakfast and tea of her mistress for the purpose of loot and theft. The lady immediately felt unconscious. Police recovered the tea samples which was consumed by the lady. Then MLR was done and blood samples along with the tea samples were sent to us for examination. Now you know here we are having a biological sample and here we are having a one food sample. So the strategy for tea sample and biological sample would be more or less same. You take tea sample around 2 ml, then centrifuge, because tea sample, it is having some particles, the leaves and some other particles of the tea and milk, they will be floating. So in order to get clear liquid for extraction, every time just centrifuge the sample, you will get a clear supernatant liquid. So supernatant diluted with basic buffer. Why we have diluted with basic buffer? Because according to the experience, whenever some compounds are mixed in the food material, they are generally benzodiazepines or sleeping pills, so that the victim can feel unconscious. Now we have extracted the sample by chlorobutane and chloroform, then analyzed by GC mass. You will see this is the total ion chromatogram of T samples. We got a caffeine, peak of caffeine at 4 minutes, and we got a peak of lorazepam. So lorazepam is basically a benzodiazepine drug. It is used in sleeping pills. So major ions of the lorazepam has been confirmed by the library 239, 274, 303. Okay, so this is caffeine. Caffeine is present in T sample, and lorazepam. Lorazepam, obviously, T sample does not contain lorazepam. So we have reported lorazepam along with caffeine. And the same lorazepam has been confirmed at the same retention time in blood sample of the victim. The blood sample of the lady who has been looted by by her maid. So the blood sample has also got confirmed by for the presence of lorazepam. Now, this is again a unique case of strychnine poisoning, accidental case of strychnine poisoning, gastric lavage. Strychnine, all of you know, it is a poisonous plant. It is known as Strychnus nux vomica, or in Desi Bhasha we call it as kuchla. Okay, so the seeds of the strychnine, these seeds look like this, and you can purchase. They are freely available. You can purchase on Amazon also. So a 3-year-old boy accidentally ingested a herbal medication. The medication was containing strychnine. By the medicine was used by his mother for skin allergy. On inquiry, mother sowed the seed of the herbal remedy that is labeled as kuchla. Child was under treatment and his blood samples were sent to our laboratory for toxicological analysis. Now you see, this is the role of, now this is not forensic toxicology, this is clinical toxicology. Okay. When the victim is alive and for his treatment, it is necessary to know that what he has consumed, what drug or poison he has consumed, and what is the amount of that drug and poison. In that case, it is known as clinical toxicology. It is not forensic toxicology. So, what were the results? Strychnine was detected in the blood sample of the patient, and results were compared with by GCMS and strychnine. We have detected strychnine at the concentration of 12.9 mg per liter. That means 13 ppm and 13.4 ppm by GCMS by DLLME. Actually, it is a paperwork also. So you can see this is the peak of strychnine by GC mass in the blood sample, or gastric lavage of that kid, and it has been detected as 12.9 minutes. And the mass to charge ratio, the base peak of 334, that is particularly for strychnine, has been identified by the GC mass. So GC mass, it is a technique for unambiguous identification. After GCMS, there is no space of doubt. There is no space of any kind of unclarity in your results. Like DNA is highly specific for identification. Likewise, GCMS is also highly specific for identification. So coming to the conclusion, the nature of cases in forensic toxicology is unique for every case. Okay. There is no single approach of analysis which can work on every case. There is no single approach. You can receive variety of samples you can receive. So you have to adjust or you have to fine tune your sample preparation protocol, your analytical strategy. And reading the statement, reading the post-mortem report, read, reread, and reread. It will give you a crucial cue about the unknown poisoning. Always in the statements of the legal heat or in the post-mortem report, there is always some clue of the poisoning. The trace amount of the analyte is sometimes poses a greater challenge to the analyst. Okay, like you have seen in the case of that lorazepam poisoning. Lorazepam was very much abundant in T sample, but it was at very low concentration in blood sample. So the trace amount of the compound is a challenging task, because your suppose your techniques are very much sufficient to detect, but you are not able to extract that trace amount, then it will be a problem. Your case will be negative. So this is a very challenging aspect of forensic toxicology, and modern sample preparation techniques can overcome that aspect. That's why I've told you that sample preparation is the most crucial in order to get reliable results. Sample preparation is most crucial. If you are not able to extract lorazepam from blood sample, okay, the FIR, the DDR, the statement all clearly indicates that the tea has been consumed by the lady and lorazepam has been detected in the tea sample. But if you are not able to detect that lorazepam in the blood sample of that lady, then it will raise question on your sample preparation. It will raise question on your analysis, how you have extracted, and you will not be able to defend your reports in the court. Then technical know-how of analytical instrument is cherry on the cake. So in our in my next lecture of pesticide, you will know how the technical know-how, how the knowledge, deep knowledge of analytical instruments will help you to solving the case. Okay, you will have a very good history. You will, each and everything is clear from the case history, but you will not be able to detect a compound which is being projected by the investigating agencies and by the doctors, but you will not be able to detect because there are some factors that we will be discussing in our next lecture. Then meticulously case study, as I already repeated, statements, post-mortem report, medical legal report is necessary for giving a direction to the analysis. Although uh, it will not completely solve your case, but it will show you in which direction you have to perform your examination. Okay, if suppose if there is a statement that the victim has vomited before death, then you can go for OP poisoning, then you can go for phosphide poisoning. Okay, so these are the statements which are very much helpful in saving your time, because whenever you will be getting in a forensic laboratory, you will know that how much case burden is there. So this is very much important. And so with all that, I end my presentation. Thank you very much. Thank you very much. Any questions? If anyone wants to ask any question, then I will be happy to answer. Only 45 participants are there because it's too late.